So let's look at number 5 and 15.1 just really briefly. So that thing's f of x and y is x to the 6th plus y to the 6th, right? Okay, and they tell me this thing has a critical point at 0, 0. And I'm supposed to classify this critical point. What the heck? Turn off. So if I'm supposed to classify the critical point at 0, 0, what do I need to do?
Double derivative?
Yeah, I need the second derivative test, right? So you go calculate d. And in this case, you find out that, all right, fx is 6x, fy is 6y, right? So fxx is,
6x to the 5th?
thank you, 6x to the 5th, 6y to the 5th.
Oh, okay.
So fxx is 30x to the 4th, fyy is 30y to the 4th, and fxy is 0. Okay, so when I calculate that d thing, right? So d should be what? 30x to the 4th times 30y to the 4th minus 0 squared, right? You guys all good on that? Okay. And then where do I care about evaluating d?
0, 0.
At the critical point, right? 0, 0. Okay, so I get 0. So this is at best kind of inconclusive, right? You guys with me on that? Crap. So what are you going to do? Yeah, you can plug in some points, you can look at a graph. I'd probably try sketching a contour line, or a bunch of contour lines. Or I might just think to myself a little bit, and this is a shitty thought and doesn't always work, okay? I want to preface that. I might think that this is x cubed squared, right? And I might think that this is y cubed squared, and I'm adding these together.
So it looks like an elliptical parabola?
Well, kind of. If I have like some kind of x coordinate squared plus some kind of y coordinate squared, what does that like remind you of? Yeah, it reminds you a little bit of a circle, right? If this was an x and a y, like if I thought about this as like maybe new x squared plus new y squared, this is like some kind of a radius squared thing, right? You guys all see that? Can I actually do that here? No. But if I draw the level curves, I'll find out that these look kind of like circles. Was I talking? Oh, I was talking with you, Dennis, the other day about this. Instead of doing like x squared plus y squared as some constant k, what if we did like x to the n plus y to the n is some constant k? And we were talking about what happens as you send n to infinity. So for the case of n is 2, this is a circle. For the case of n is infinity, this is a square. And for other cases, it's something in between. So for x to the 6th, it probably looks something like this. You guys see that? So my set of contour lines, right, is going to look like nested these guys. You guys see that? So like this might be my, say, Z is 1 contour line. Really, I'm kind of thinking, take n is 6, set this equal to 1 and solve. You'll get some shape that looks a little bit like this. And then you'll get other shapes at other contours that are kind of off squares, right? You guys cool with that? Okay, so I feel like I could maybe say that this is a what? What do I think this sucker is?
A minimum.
It's probably a minimum. You guys see that? Can I say that with the tools I have in Calc 3? Yeah. Right?
Yeah.
I don't really have a good conclusion to say, yeah, it's definitely a minimum. I have the second derivative test doesn't work. I don't have another test outlined somewhere that I know about. But I feel like I can shake this picture at it hard enough to say that this thing's a minimum. So minimum because reasons. You guys recognize what's special about that kind of minimum versus the kind of minimum we were seeing the other day? Yeah, this one's actually global, right? What's the difference between global and local?
Global is the entire thing, like the whole graph, and local is at a certain.
Yeah, so in the local minimum direction, or definition, right, I had AB is a local minimum if f of AB is less than or equal to f of x and y for x and y near AB, right?
Mm-hmm.
So to make that definition global, what piece of that do you chuck?
Near.
Yeah, the near AB, because if it's global, it doesn't matter where you are, right? So you just pitch that. Cool? Questions, Steels?